Good morning, students.
Morning.
Good morning, ma'am.
So we'll start at 10:45. Today, no placement, right?
No, ma'am, there's an exam today. That's why I think the strength is also less.
Less means it's very less, na? Only 5 it is showing, right?
Yes, ma'am.
Which exam is there today?
Josh Technology.
What time?
10:30 it started.
Oh, okay. Actually, your class advisors do inform us. They informed us about all the placement going to happen in the month of August, but I didn't see that, in detail. Okay. So what do we do for the class? So we will have the class anyways. I am recording it, right? Because you people are extremely busy, and then uh, it will be difficult to schedule the class some other time, right? So, shall we have the class? Anyways, it's not whatever we are doing kind of revision only. So we'll continue with the class. Let them join as and when they come. Right? Is it fine, students? The exam is for what is the duration of the exam? It starts at 10:30 and then?
Not sure about it, ma'am.
So everyone is not writing that, right?
People who applied will be writing for it.
Okay.
Most of them would have applied.
Okay. Okay, so let me wait for 2 more minutes and then we will start. Yeah, there is another announcement that maybe you can discuss among yourself, or anyways we have a group, so I will also put there. The announcement is we had a class committee meeting on Saturday. Okay, so it was decided, I mean, we were suggested that since students will be busy, you people will be busy, so for final year students, the suggestion was that we will have only 2 quizzes, quiz 1 and quiz 2. So the earlier plan was to have 3 quizzes, right? So now what was proposed was, what was finally decided was, we will have one quiz before mid-sem, and we will have another quiz after mid-sem. So 10 marks each. I mean, I can make it 15 and reduce to 10 also, but the weightage is 10 marks rather than having 3 quizzes. But then I will have third quiz also, Q3 also, that will be, and then we will take best 2 out of those 3 quizzes. So that if, basically we will try to have the quiz when all of you are present, right, in AUMS. We can anyways, we will try to do it during the class hours, or otherwise other the class hours also, where all the students are present, so that all of you can gain the advantage of writing all the 3 quizzes. But in case, for any kind of discrepancy in AUMS or something, or one student has missed a quiz, so the quiz 3 will be helping there. Okay, but quiz 3 will be including the portion of quiz 1 and quiz 2. So we will take best 2 out of those 3 quizzes. That was one thing that was decided for our course. What else? That was actually decided for all the courses. Actually, all the courses will follow the same thing. What else was decided? Yes, one more thing was decided, that uh, your T1, midsem will be, the midsem written will be happening for 30 marks. That will be reduced to 10 marks. And Viva will be 20, and it will be for 20. And end semester will be for 50 marks. That will be reduced to 20. Okay, so earlier I had planned to make it 35 marks, so it has to be 50 marks. So I will update that. Okay, I will update it. It is almost, same for all the subjects. So any subject tells you it is same where we are following 50-50. So I will anyways update it. And, the dates had not come. Earlier when I had made the course plan, the calendar had not come. So I thought that, midsem will be towards the end. So accordingly, I had made the plan. But now midsem is not towards the end. It is actually during the mid of the semester. So much portion will not come in midsem. So I will update the plans to you. For that, I have to open the calendar and sit, one day I should find time. So I am also running little busy nowadays because we are winding up second semester and I am involved with 3 courses of second semester right now. So once that gets over, after 15th, after 18th of August, I will make another plan, seeing the calendar, and I will pass it to you. Okay. Anyways, the lecture-wise plan will remain the same. The sequence of lectures will remain the same. Okay, so only one quiz that will happen before midterm, one quiz before end semester. After, not before 1 month before end semester, and quiz 3 we can have just before end semester. Okay, so I think I will start now. I have waited enough for students. Now 20 students are there. All right. So anyways, they can see, they need not even listen to the lecture probably. They can go through the slides and they will be able to understand because because it's kind of revision only. All right. So all right, students. So we were discussing this. Was asking you a quick quiz. So you had told the answer for this, right? And you said that here n factorial of n and n to the power of n we were discussing, right? So the answer was that factorial of, you will say it. Anyways, this will also lead to somewhere n to the power of n. So this is going to be n to the power of n. That is what we were discussing last. And then there are some examples. These should be in our tips, right? So O1 is called as constant. Okay. So where do we use constant? We say wherever there is a fixed amount of work, regardless of the input size. We are always doing the same amount of work. For example, when you add two 32-bit numbers, you say it as it's a constant, right? When you determine if a number is even or odd, fixed amount of time, you are going to sum the first 20 elements of an array. Why this is constant? Because you are fixing the number of elements that you are going to add. You are not saying that you are going to add n elements. You are saying that summing the first 20 elements of an array. So it is going to be constant time. Okay, O1 doesn't mean that it is very less. O1 doesn't mean that it is very small. It means that it's constant. Okay, and for example, you delete an element from a doubly linked list. It's a constant amount of work, right? You have been given a doubly linked list, you want to delete an element, so definitely you are going to first search it. Once you get it, you are going to remove the pointer, right? And you are going to change the pointer, right? The next of the left hand side node becomes the next becomes the right hand side of the node. So it's a fixed amount of work. So that is why the complexity is treated as O1, constant, right? We call it as constant. And what is O log n? Okay, O log n is called as logarithmic time complexity. Okay, where exactly we do this log n kind of thing? Wherever there are iterations, and in each iteration we discard some portion of the input. Okay, generally we discard half of the portion, but even if it is not half, right? So when you do you keep on reducing the input size, you discard some portion of the input, we get a kind of log n, some variation of log n, logarithmic complexity. So there we get it as log n. Then, for example, binary search, right? And then we get a linear complexity ON. Okay, so there is a difference between linear and a constant. Linear means do a constant amount of work on each element of the input. Okay, we are doing constant amount of work, but that is for each element of the input. So as you grow to the input size, because At each input you are going to do some work, it is going to be linear. That is going to be ON. For example, find an item in a linked list, right? Finding an item in the linked list. So depending on how many elements are there in your linked list. Okay. For example, determining the largest element in an array. That's a constant amount of work. That's a linear amount of work. Okay, I go back to previous slide if someone had a confusion. Here I said deleting an element from a doubly linked list is a constant, right? And here I am saying that finding an item in a linked list is linear. Okay, both the statements are correct. Okay, because when I am talking about deleting an element from a doubly linked list, I am not including the searching that element in the linked list. Okay, searching that element is linear, but once I have found the element, then only deletion. Already the location is given to me that which element I want to delete. Okay, if the location is given to me which element I want to delete, it's a constant operation how to delete that element. You just have to update the pointers, right? But here we are talking about searching an element, finding an element in the matrix, that is linear amount, because simple logic, you want to find an element, you have to check with each of the node of the linked list whether the item is there or not. Each of the element I need to find, but once I have found out, just deleting is a constant amount of work. Okay, so then determining the largest element in an array, you have to visit all, so it is linear amount of time. Okay, then there is something called as log linear. That is linear, a combination of linear and a log, right? So log linear is, it uses, it comes in divide and conquer kind of algorithms, wherein first we divide the problem. So when you divide the problem, you get it as a log n. There is a concept of getting what is the tree, tree depth of the tree. You keep on dividing the problem, and finally for recombining the solutions you need a linear amount of time. Okay, so divide and conquer, the dividing phase takes log n time, and linear amount of work is required to recombine the solution. So those are called as log linear kind of problems. Okay, for example, sorting a list of numbers with merge sort. Okay, or fast Fourier transformation. This we will see fast Fourier transformation in our advanced algorithm towards the end, unit 3. Okay, so some another examples. ON square is called as quadratic. Okay, so all of you know that wherever you have double nested loops that iterate over the data, right? Therein you are going to get the n square kind of complexity. Insertion sort, that is what we are going to discuss next. Insertion sort, all right? So then exponential, O2 to the power of n, for example. It can be anything, 3 to the power n, any integer power of n. Okay, so where do we get such kind of complexity is wherever we have to enumerate all possible subsets, right? So there is a, that, for if there are n elements, then how many subsets you can make the power set, how many subsets you can make 2 to the power of n, right? So, and then similarly, for traveling salesperson's problem using dynamic programming, that also has an exponential kind of problem. So those examples we will be seeing. Then O factorial of n, right? Factorial of n, where you see again enumerate all permutations. Okay, for example, when you have to find the determinant of a matrix with extension by minus, therein you are going to get such kind of complexity. These are, this is a table again taken from the book. Okay, it is in the book. So these are some of the runtime examples. If you see n log n square, n cube, 2 to the power n, and factorial of n. Factorial of n. So n is equal to 30, n is 20, 10, 30, 100. The n is getting increased here. And accordingly, there are variations. Right? So now if you see, let us take this example, n is 100. So complexity n, for example, you have an algorithm that takes less than 1 second. N log n also takes less than 1 second. N square takes 1 second. N cube takes 1 second. 2 to the power n complexity takes 10 to the power of 17 years. And factorial n takes very long, means we are not able to calculate it. Right? So we see the difference. We actually see the difference when the value is really large. Now if you see for 10, 30, when it is linear, it is all less than 1 second. When it becomes 1 million, then only you see it as 1 second. Right? And similarly, you see how it changes. For n square, till it is 30, it is just less than 1 second. For 100 and 1000, it is just 1 second. For 10,000, it is 2 minutes. And when you increase, when you go to 1 million, you see it as 12 days. That becomes the complexity. So you can see it here that it is when it is factorial of n, and when you make n is equal to 30, it is going to come, the complexity that you are able to solve is 10 to the power of 25 years. Very long time. Very long time, because we don't want to say infinite time. But it is almost like, we are not able to compute how much it is. It is very, very large. Okay, so this is just a table, just to understand, to figure out how with the changing the size of input, how these time complexities are going to vary. Okay, so now we will take an example for understanding insertion sort. Okay, so there are various sorts. We will discuss merge sort also after this. So we are talking about insertion sort, and we are trying to understand how the complexity is going to be O n square. Okay, and then we will also see that can we reduce this complexity. Okay, so I will ask you a question. So the answer is yes or no, that you will be telling me. If you say it is no, why? If you say it is yes, then also why. Okay, so let us first understand insertion sort. All of you must be remembering that what is an insertion sort. Okay, but so do not think that I'm just going to tell what is the insertion sort. After doing the insertion sort, we are going to talk about one important definition. Okay, and whenever we see any algorithm, okay, what exactly are we trying to define in that algorithm? Okay, so that is what we will see. So for that I am taking an example. Okay, so let us just see the example, and then we'll try to see. We'll first see the insertion sort. We will do one example, and then I will what is the takeaway I'll be telling you. Okay, so now when we see the algorithm, our perspective of seeing the algorithm has to be that way. Okay, so we will discuss that. So I have an insertion sort A. Okay, so insertion sort A means this. I told you, right, that writing the algorithm is instruction. The name of the algorithm and then the input. So that we have not written here, but we must write that the input is given array A, and output is the sorted array A. We must write that. And there are 7 lines in the algorithm, 1 to 7. Okay, so and here we are starting the index of the array from 1, not from 0, for simplicity purpose. Okay, in all the algorithms given in our book and in our course, we will be having the array index starting from 1, not from 0, students. Okay, that is for the simplicity. Okay, we can treat it as 0 also. There is no harm, but this is for the sake of simplicity. We are assuming the array index starting from 1. So if there are n elements, means index is from 1 to n. Okay, so that is why, see, we are starting from j equal to 2. Okay, so what we are doing? We are doing insertion sort. So there is first element. We are saying for j equal to 2 to length of a. We don't know what is the length of a. So rather than saying n, we are saying for j equal to 2 to length of a. What we do is current we make as aj. That is the second element of the array we are making as current. And then we are making I equal to j minus 1. So my I will become the index of the very first element. So I want to now compare these two elements, right? So while I is greater than 0, right? I is greater than 0. So I will be greater than 0 because I have made I equal to j minus 1. So I will be 1. And AI is greater than current. AI is greater than current means AI is A1 is greater than current means A2. If A1 is greater than A2, first time this will happen. If it is happening, then we are exchanging. AI plus 1 becomes AI. Okay, not exchanging. We are making the second element, AI plus 1, becoming the first element. We are making it to place at second element. And then we are making I equal to I minus 1. Right? Why I am making I equal to I minus 1? Because I know that I have made I is greater than 0. Right? So I will reduce it. So what will happen for the first time? I will become 0 and this condition will not satisfy. Right? So first time we are only comparing two elements. So it will come out of the loop. And because I know we had entered into the while loop, and then we are making ai plus 1 becomes the current element, right? Ai plus 1 becomes the current element means ai plus 1 means a2 is going to become the current element because the current element we had made as a2. Okay, so the same algorithm. So this is how it works. So I have put it here, don't worry. Okay, so let us see. Okay, so let us take an example for this. Okay, so wherever possible, students, I have tried to create the example to see it properly. Okay, so now this is what is given. So we write here indexes a1 2 3 4 5. This is the index and this is the given array. So we have taken a small example so that it is easy to understand. This is the array 26 39 15 45 and 3. Purposely we have kept the last element as the smallest element. Now let us see how this is going to work. Okay, how the algorithm is going to work. So initially we have said j is equal to 2. Okay, j is equal to 2 and my current will become 39, the second element of the array. Okay, and then what I do, I is equal to j minus 1. So I becomes 1. I becomes 1. Now it goes to the loop. Okay, I is greater than 0. Yes, I is greater than 0 and ai is greater than current. A1 is 26. Is it greater than current? 39? No. It is not greater than current. So it doesn't go inside the loop. Right? It doesn't go inside the loop. So there is no change. There is no change. But then it says ai plus 1 becomes current. So ai plus 1 becomes current means a2, ai plus 1. I was 1, so a2 becomes 39. Fine. So you will not see the change, right? But this is there. ai plus 1 becomes current. It doesn't go inside the while loop. It doesn't go inside the while loop. It comes out of the while loop. Okay. Then what happens? After that, the value of j has to be incremented. There is no change. So this is what is your array. After the first iteration, when you made j is equal to 2, there is no change. Because you compare 26 and 39. Current has become 39. See how we are starting. We are starting from index 2. Now we are making j will become 3. J is from 2 to length of a. That means 2 to 5 it is going to go. So now j becomes 3. When j becomes 3, the current becomes 15. Current becomes aj. Current becomes 15. And now I will become, I is j minus 1, right? So now I will become 2. Right? I will become 2. Now I is greater than 0. Yes. I is greater than 0 and ai is greater than current. What is ai? ai is 15. Okay, that is greater than current. ai is 15, that is greater than current. Sorry, uh, ai is 2, so ai is 2, a2 is 39, right? A2 is 39, that is greater than current, that is greater than current. Yes. So what we are doing, we are making ai plus 1, that means a3 should become a2, right? It is going to go inside the while loop, so a3 should become a2, right? So this has happened. A3 has become A2, but there is no change to A2, right? A3 has become A2 and I has become I minus 1. So now I has become 1, right? I has become 1. Still it is inside the while loop, while I is greater than 0. Yes, I is greater than 0 and AI is greater than current. So now what is A1? A1 is 26. That is also greater than current, right? 26 is greater than 15. So again you have to do ai plus 1 becomes ai. That means a2 should become a1, right? So this is what should happen. So now 26 has come here, right? Now you will make I equal to I minus 1. So I will become 0. Now it has to come out of the while loop. And then your ai plus 1, that is, now I has become 0. So ai plus 1 means a1 should become as current. So now your a1 has come as 15. Right? A1 has come as 15. 15, 26, 39. So I want you to observe something here, students. Okay. So what is your observation? So when you did the first iteration, okay, when you did the first iteration, you see what is the output. After the first iteration, the output was 26, 39, 15, 45, like that. Okay. Now when you're, so So you just see it like this, okay? What is your observation? When your j is equal to 2, you started from here for j equal to 2 to length of a. When you made j is equal to 2, all right, and this is the array, this green color is the array that is your output. Okay, you observe something here. Okay, and when your j is equal to 3, this green color is the output of this iteration, j is equal to 2. There is something to be observed. You observe that. Okay, then now what happens? I will not say what is the observation. You have to observe and tell me. Okay, then we say j is equal. Now what will happen? Now j will become 4. J will become 4 and current will become 45. Right? So now what happens? I make I is equal to 3. Right? So now we have to check AI is greater than current. AI means A3. A3 is greater than current? No. A3 is 39. It is not greater than 45. Right? So it will not go inside. There is no change. Right? And then we will say AI plus 1 becomes current. AI plus 1 means A4. No, sorry. After that will not happen. But again, again it has to check for the next element, right? So first time J becomes 4, I becomes 3. Right? J becomes 4, I becomes 3. There is no change. Right? But then your I will become 2. Right? I will become 2. So when I becomes 2, sorry.
I will not become 2 now, ma'am.
Why? Yeah, right. I will not become 2 because it is not going inside. So there is no change. There is no change. It will come out. So it will become AI plus 1 becomes current. So you don't see any change. But AI plus 1 means A4 becomes current means A4 becomes 45. It was already 45. So there is no change. So you observe again when J is equal to 4, there is no change. This is the output when J is equal to 4. Right? Now J becomes 5 and current becomes 3. Right? J becomes 5 and current becomes 3. Now we see I becomes 4. Right? So now AI is greater than current. Right? That is A4. 45 is greater than current. So what you do is this 45 will be placed here. Right? AI plus 1 becomes AI. So 45 has come here. Right? Then I becomes I minus 1. I becomes 3. Right? Again, you check that A3, that is, what is A3? A3 is 39. That is also greater than current. Right? So this is the change that you see. 39 is placed here. Now again, I becomes 2. Right? I becomes 2 means again, this AI plus 1 becomes AI. So this becomes 26 comes here. Then again, I is 1. Again, there is a change. Right? When I becomes 1, again this is a change, and finally you get I is equal to 0. So when you get I is equal to 0, this is what you get finally, right? 3, 15, 26, 39 and 45. Finally when I becomes 0, this is the output, right? So because we had made the last the smallest element at the end, so every time there is a change. And this I forgot to color it, so this should be 15, should also be with red color. So this should be 15 is going to come with a red color, and finally you are going to make it like this. Okay, so what is the observation with respect to J? Okay, so when J is equal to 2, this is the output. When J is equal to 3, this is the output. When J is equal to 4, this is the output. When J is equal to 5, this is the output. What is the observation, students? Okay. So what do we see here? Okay, probably we are not able to put it in words. So when J is equal to 2, the output that you see has the first 2 elements of the array sorted. Right? First 2 of the elements sorted. Not the whole array sorted, but you see when J is equal to 2, 26 and 39, they are sorted. When J is equal to 3, first 3 elements are sorted. 15, 26, 39. When J is equal to 4, first 4 elements are sorted. 15, 26, 39 and 45. And when J is equal to 5, all the array elements are sorted. Right? So you know why that's how we differentiate different kind of sorting mechanism, because every sort has a different style, right? they are standard algorithms. So insertion sort means it has to be like this, right? So this is a important observation that we saw. Okay, what was the observation? That whenever you write the loop like this for j is equal to 2 to length a, you start with index 2. So what is the value, the starting value of the loop? When you say 2, the output of that iteration is the two elements of the array. First two elements are sorted, next two elements. Whatever is the value of j, those many elements of the array are sorted. Okay, that is an observation. Just keep it in mind. Okay, so the next question is for any algorithm. I never discussed that. When we discuss the algorithm, there are few properties that an algorithm should have, right? The algorithm must terminate, right? Algorithm must terminate. So the question is, does it terminate? We saw that yes, it does terminate, right? And then we also say that another question to be asked for any given algorithm is the algorithm correct? And if you say it is correct, then you have to prove it. How will you prove it? Can you prove it? There are various methods to prove the correctness of the algorithm, right? So let us say we will learn them by few examples. Can you prove it? Yes, we can prove it. Okay. This is one definition that we must understand, that is known as loop invariant. Okay, so what is the meaning? What is the definition of loop invariant? Loop invariant is a statement about a loop. Okay, that is true before the loop begins and after each iteration of the loop. Okay, so what is a loop invariant? Invariant, as the name indicates, that this is not going to change. It is a statement that will remain true before you enter to the loop or after you enter to the loop. Okay, a statement about a loop that is true before the loop begins and after each iteration of the loop. Okay, upon termination of the loop, the invariant should help you show something useful about the algorithm, right? So now probably you are able to link what I said, the statement, the observation that I made. I asked you to note down about the algorithm insertion sort, right? Before entering to the loop, the statement is true. Right now, the value of j, you are starting with value as 2. But before entering to the loop, let us say if the value of j is 1. If you keep it as 1, that means you are saying that only one element of the array is sorted. Fine. When you make j is equal to 2, now you are able to make a statement that whenever whatever is the value of j, at the end of that iteration, at the end of that particular iteration, those many number of the array are sorted. That is a loop invariant. Okay, so we must be able to find a specific property about the algorithm, about a loop if you are entering, such that this is something specific, something useful about that algorithm that is constant before you enter to the loop and after each iteration of the loop. That is not constant, that is true. I must say that is true before the loop begins and after each iteration of the loop. That is what is called as loop invariant. Okay, so here what is the loop invariant? That is what we discussed. So the loop invariant is at the start of each iteration of the for loop of lines 1 to 7. Now it is written properly. At the start of each iteration of the for loop line 1 to 7, the sub-array A 1 to j minus 1 is the sorted version of the original elements of A 1 to j minus 1. Okay, so whatever I said, that is put it in algorithmic terms, right? So that is what is the loop invariant here. At the start of each iteration of the for loop of lines 1 to 7, the sub-array A1 to j minus 1, right, is the sorted version of the original element of A1 to j minus 1. Same thing. So when you say j is equal to 2, so you are saying that A1 to 1 is the sorted array. When you say j is equal to 3, when j is reaching 3 means just before reaching 3, right? So A1, 2 are sorted. After 3, A1, 2, 3 are sorted. That is what is your loop invariant. Okay. So what is the proof of it, right? How do we prove it, right? So many methods are there. One method is so suppose a loop invariant is given to you, okay, and you say this is the loop invariant. So how do we prove? So you know one of the very popular, very nice method of proving is proving by induction. Right? So what do? We prove. So we have a base case. So for induction, we say that invariant is true before the loop because that is what is your assumption, right? And then in inductive cases, we say that it is true after loop cycle. So generally, we say that true by induction. We say that it is true for base case, and we assume that it is true for case I, and then we say that then we show that it is also true for the case I plus 1. Right? So whenever needed, we can prove these loop invariant by proof by induction. We can prove that, right? So another thing. Now the next question is how long will it take to run? Right? How long will it take to run? It looks only one for loop, right? It looks only one for loop, right? So what will be the complexity students? How will it take to run? If you say O n square, then where does that n square term come?
From the while loop, ma'am.
From the while loop. Yes, from the while loop, right. So how long will it take to run? You know that the complexity is going to be O n square because every time for this j you are it's like for j and then you are again, this is n set for j, the value, if the length is n, j will vary from 2 to n, and similarly you are checking I is greater than 0 and so I is greater than 0 every time you are going to check, and the value of I is reducing, right? I is equal to I minus 1 because this I is dependent on j. So you saw when j value was 5, so we had, and every time when the condition satisfied, we had to make I became 4, I became 3, I became 2, I became 1. You saw that iteration, right? Because I is becoming I minus 1. So in the worst case, this was also a worst case, right? So this was a worst case that we considered. We considered a worst case wherein the last element was the smallest, right? So for that, it took all the values, I equal to 4, 3, 2, 1, and finally it became 0. So in the worst case, if you have n elements, so there will be all iterations. So n into n, the complexity is going to be, it is going to be a quadratic complexity. Okay. So I have not put it in slides because you know that, right? So what is the intuition for asymptotic notation? This is the last slide for the for the asymptotic notations part 1. This is the lecture 2. This is the last slide. Just intuition for asymptotic notation, right? So you already know. So we say that Fn is big O of Gn if Fn is asymptotically less than or equal to Gn. You know Fn is less than or equal to O of Gn. You know for some constant C. C. Fn is less than or equal to C of Gn. Right? C has to be a positive constant for all n is greater than or equal to n0. Right? N0 and C has to be positive constant. Big omega, Fn is big omega of Gn if Fn is asymptotically greater than or equal to Gn. Greater than or equal to, less than or equal to. Theta means it is asymptotically equal to Gn. So theta means it is O of Fn as well as O of Gn. Then little o. I only thought I will only speak this much about this little o and little omega. They are not much used. So little o is similar to big O. Fn is O of Gn if Fn is asymptotically strictly less than Gn. So it is, if you see the two definitions, these two are same. Only when you say small o, you say strictly less than. Strictly less than means it cannot be equal. Right? It is less than, strictly less than G. So the case where you say that it is equal, that is not considered in little o. Right? So if that equal case will not come, means it will not be theta also. Because for theta you want to get the equal case. Similarly, little omega is Fn is little omega of Gn is, excuse me. Fn is small omega of Gn if it is asymptotically strictly greater than Gn. So it is just greater than that, greater than or equal to theta does not come. Okay, so that is what is the end of these slides for L2 analysis of algorithm part 2. So that was just a revision. So now we start with recurrence. Okay, we start with recurrence. We have time, right? The class is still what time, students? 11:35. No, we have time.
Yeah, 10 more minutes now.
Yeah. Okay, so recurrence part 1, recurrence we have divided into 2 parts. Okay, so again we will take example of merge sort here. Okay, so we will first start with the general concept of recurrences, right? So we understand recurrences with the terminology of divide and conquer, right? So what exactly it is, what exactly divide and conquer problems are. Divide says that break the problem into smaller sub problems, okay, and conquer is solve those some sub problems. Okay, generally this involves waiting for the problem to be small enough that it is trivial to solve, only 1 or 2 items. Okay, so finally, suppose I want to do a sorting, right? So I reach to extent that there are only 2 elements, right? Because it is easy for me to sort the 2 elements. Just I have to do one comparison operation. Or further, for that also I can lead it to only 1 element. Okay, 1 element means it is already sorted, right? So that is the idea, that you divide the problem into so small sizes that it is easy to solve the smallest subproblems. But once I have solved all those smaller subproblems, combining means we are given the results of the solved subproblems. Subproblems are already solved. We have to combine them to generate a solution for the complete problem. There is an algorithm that has to be applied for the combining also, right? Simply I cannot put all the combinations, right? So the algorithm has both the steps. First divide, 3 steps basically: divide, then solve those smaller problems, and finally combine the solution. Okay, so often the sub problem is the same as the original problem. In general, divide and conquer kind of problems, the idea to divide is, after dividing you are not trying to solve a different problem, right? You are trying to solve the same problem. So it sometimes it is like you have a big problem. That problem you solve in 3 steps: first step, second step, third step. That is also dividing a problem, but those sub problems are totally different, right? If it is a step 1, step 2, and step 3, right, that is different. But in general, in divide and conquer, what we mean is that sub problems are also say similar to the original sub problem. Okay, and dividing the problem in half frequently does the job. Okay, and may have to get creative about how the data is split. Sometimes we have to be very creative that how do we divide the data among the sub problems. Okay, and splitting tends to generate runtimes with log n in them, that you would have seen. We will take one example also. How do we say that once you split the input data, you tend to generate log n times? Okay, so one approach is pretend like you have a working version of your function, but it only works on smaller sub problems. Okay, one approach of divide and conquer is, we will assume that, okay, I am able to solve this problem, but you are asking me to sort, let us say 10,000 elements. No, but I can sort only 2 elements. Okay, I can solve. So similarly, so I have a solution for the given function, but only for smaller subproblems. Okay, and so if you split up the current problem in some way, that is into half, and solve those subproblems, okay, then the next question is, how can you combine? How could you then get the solution to a larger problem? So it's not that simple, the combining is again not very simple, that I just put all the solutions together. There has to be one algorithm involved for combining the solution of smaller subproblems. Okay, so the next question is, how should we split the data? Okay, and then what are the sub problems we need to solve? If, let us say, one of the problems of divide and conquer, the popular problems of divide and conquer is sorting algorithm. Okay, so how should we split the data, and then what are the sub problems that we need to solve? The sub problems are again going to be sorting problems, and the next question is, how do we combine the results from these sub problems? right? So let us take an example of merge sort, very popular sort. All of you must be knowing this. Okay, so again, we have not written here input output, but that is a must. We must write that merge sort array A. Input is an array A. Output should be the array A sorted. Okay, and this is a small case that we have written here. You know, it's like you can say it's a base case. Okay, so this is the merge sorting algorithm already written, which is going to work on divide and conquer principle. It says that if length of A is equal to 1, right? If the array A given is 1, so I return A. That means if there is only one element, that is already sorted. Else, for any other length, first we find out Q as what is the half. Q as a number, as an integer, you know, you are taking a floor of it. Okay, that is A by 2. Why we had to take this floor? Because the array length may not be even. Okay, so Q becomes length of array A divided by 2, floor of it. Okay, so the if it is 3.415, so I will take Q as 4. Okay, and then what we do is we create two arrays named as L, that is the index 1 to Q. I told you, right, that array indexes all we are assuming will be from 1. So we create arrays, two arrays. One we call it left array L, 1 to Q, and right array R, Q plus 1 to length of A. Okay, so then what we do is we copy array A 1 to Q to L. Okay, first you are creating two array of this much size, then you are copying array 1 to Q to L and copying array A Q plus 1 to length of R to R. So you can say that you are dividing the initial array into two parts, left and right. And then you again call merge sort L. Now this is important. See, you are recursively calling merge sort L, and this algorithm itself is merge sort. So rather than saying merge sort A, now you are saying merge sort L, and the output of that you put as LS. That is left hand side sorted. And then merge sort R, the output of that you put in RS. That is right hand side sorted. And then you are going to return merge of LS and RS. Now the important point here is merge sort is one algorithm, merge is another algorithm. Right? This is a merge sort algorithm. So in merge sort algorithm, you can see it is recursively calling the same function merge sort, but there is one more function involved that is called as merge. That is going to merge these two sorted arrays, LS and RS. Right? So now let us see what could be the merge algorithm. What is the merge algorithm? So this is merge sort algorithm. Merge sort algorithm also uses merge algorithm in it. So what is that? Okay, so what merge algorithm assumes? Merge algorithm assumes that L and R are sorted arrays. It assumes when you say merge LS and RS, it assumes that the two arrays that it is going. So the input of the merge algorithm is it has two sorted arrays, LS and RS. Both the arrays are sorted, and the algorithm is going to merge those two arrays. Assuming L and R are sorted already, merge the two to create a single sorted array. That is merge LR. Okay, so first of all, of course, you are going to create an array B, output array. So the input is two sorted arrays L and two L and R with this length. Length of array L is L, length of array R is, you can say it is already given. So the first step we do is we create an array B that is going to be my output array of length. The length has to be combined length of them, length of L and length plus length of R. Then you make I is equal to 1 and j is equal to 1. Right? These are going to be the two indexes on which we are going to work to merge the two arrays. Okay. Now what is k index? K is the index that is going to work for the output array. I is the index that is going to work for array, the left hand side array. J is the index that is going to work for the right hand side array. And k is the index that is going to work for the output array B. So that is why k will be moving from 1 to length of B. And you will initialize I to 1 and j to 1. Right? So the algorithm is very simple. What you do is you actually check. So you have two arrays, right? So basically you will first check the arrays are sorted. So you will see the left hand side array and right hand side array. So you will pick the first element of left hand side array that you should match, you should compare with the first element of right hand side array, right? Whichever is smaller, if whichever is smaller, that you are going to put in the output array, right? Suppose the first element of left hand side array is smaller than the first element of the right hand side array, right? So what you do is you are going to put that element as the first element of the output array. Then you should increase the index of the left hand side array, right? But right hand side array index you are not going to touch, right? Then you are going to check the left hand side array with left hand side array next element you are going to check with the first element of the right hand side array, right? Like that you are going to traverse the indexes of the left hand side array with I and right hand side array with J. So as soon as you put a corresponding element of left hand side or right hand side to the output array, you are just going to move that index. That is what we have written here. For k equal to 1 to length of b, if j is greater than length of r, this is for the terminating condition. If j is greater than length of r, j means j, because you have made it as 1, right, is greater than length of r. When it is greater than length of r, obviously it is not going to be more than length of r initially. But this we have made for the condition to be terminated, right? How long we should search in the next array. That is why we have made j is greater than length of r. Or this condition will satisfy. I is less than or equal to length of L and Li is less than or equal to R of J, right? When I is less than or equal to length of L, so till in the left hand side array, the element Li is less than or equal to R of J. Till then, what you do is you keep on putting the elements from left hand side array to the output array. So Bk becomes Li and you keep on making I equal to I plus 1. Right? That is what is the idea. What we do is we start with the left hand side array, okay, and we check. We find that left hand side array elements are less than the right hand side array. We keep on putting them in the output array. But as soon as that does not happen, right, either we are done with all the left hand side array or this is not less than, we do not go to the if loop. We will come to the else loop. And now we will copy from the right hand side array to the output array. And then we are going to keep the index. We will increase the index of the right hand side array. All right. So we'll continue with this, students, tomorrow with the help of an example. Okay. And then we will also talk. Then we will actually, after seeing this merge sort example, we will talk about the recurrences in more detail. Okay. So thank you, students. We'll wind up here for today. We'll continue this in next class. Thank you, students. Let me see. Total 31 people only could attend. All right. All right, students. Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.